Today is the continuation of the same chapter, elasticity. Last class I taught you three kinds of modulus of elasticity: Y, K, and N. Young's modulus, Buck's modulus, and modulus of rigidity, and their formulas I gave. Today we will be doing this one, Poisson's ratio. Let us know what is Poisson's ratio. Poisson's ratio. Poisson's ratio is denoted by this symbol. The symbol is read as sigma. The symbol is read as sigma. Poisson ratio, first you understand and then you will do, okay. When we elongate a body, that is, we are increasing the length of the body by applying a force, like a deforming force, you will find the length increases, but the diameter of the body, if the wire is like circular wire or cylindrical wire, you will find that the diameter of the wire decreases. That means it has the effect of length on the diameter. The diameter, when the length increases, the diameter decreases, or when the length decreases, then the diameter will increase. So that's why we define this one. The change in diameter per original diameter is called lateral strain. Strain in diameter is called lateral strain, and strain in the length is called longitudinal strain. Longitudinal or lengthwise tensile strain also we can call it, tensile strain, which I have written in case of Young's modulus. So Poisson's ratio is the ratio of lateral strain to the longitudinal strain, or you can write here longitudinal strain. Longitudinal is lengthwise, or we can call it tensile strain. Sigma is equal to lateral strain formula, change in diameter per original diameter, and this is also kind of a strain only, so change in length by original length, and we put a minus sign because increase in the length causes decrease in the diameter, so minus sign, because sigma is always positive, and the value of sigma lies always between 0 and 0.5. The value of sigma always lies between 0 to 0.5. So this is the formula of Poisson's ratio. It has no unit because both of them are strain and strain itself has no unit. So there is no unit for Poisson's ratio. Now we are finding a formula for work done in the extension or elongation of the body, the extension or elongation in a body. This is only known as elastic potential energy. Okay. We are finding a formula for it, right? According to Hooke's law, within elastic limit, we see this force of elongation is F will be proportional to elongation, directly proportional to the elongation. More the force, more the elongation; less the force, less the elongation. This one we change into equal sign by multiplying constant at K into delta L. We can add delta L, delta X, any way we can add, or we can add small e means elongation. Okay, we read the graph between F and delta L is as follows. We draw the graph between force and elongation graph. Force is here, elongation is here, and the graph will become a straight line like this. If I find the slope, then slope will be the value of K, that where K is called spring constant. If it is about spring related spring constant, K is the value of spring constant. The constant is known as spring constant. So we are drawing the graph within the elastic limit. The graph will come a straight line. So area slope is equal to k. That is F by delta L. F by delta L gives the value of k. And area will give, area means force into displacement. Area will give the value of work done. Area is equal to work done in extension. Or we can call it potential energy. So here we will be writing like this. Therefore, work done in extension which we are calling elastic potential energy. Elastic potential energy will be equal to area of this graph. So area of F dash dl graph. We write like this. We'll be drawing a dotted line here and see what type of figure is formed. Triangles. We'll find area of the triangle. We write half into F into delta L. It becomes half F into delta L. So this is the formula of elastic potential energy. Elastic potential energy. Elastic potential energy we can denote by symbol U, capital U. U formula is this. In class 10, we used to learn that there are two types of potential energy: gravitational potential energy and elastic potential energy. So you did not know the formula of elastic potential energy then in class 10. Now you know the formula half F into delta L. Okay. We find one more thing is called energy density. Elastic energy per unit volume, that is called energy density. We write like this: elastic energy per unit volume. Elastic energy per unit volume formula we have. We write like this: elastic energy divided by volume. Elastic energy formula just now we found that formula was having half F into delta L. Volume of the body formula will add area of cross section into the original length. This becomes half F by A becomes stress, delta L by L becomes strain. So this is the value of elastic energy per unit volume. Elastic energy per unit volume. Elastic energy per unit volume. This is the formula of this. Elastic energy per unit volume formula is half into stress into strain. Even the derivation may come out here. Show that elastic energy per unit volume is half into stress into strain. You can begin from this graph. The question is carrying 3 marks. You begin from the graph. First you find elastic potential energy, then you find elastic energy per unit volume this way. And your answer will become half stress into strain. Sometimes, very often they ask this question. That when we draw a graph between stress and strain out here within whose elastic limit, who said about the force and elongation also, and he said about the stress and strain also. He said that the stress is directly proportional to the strain. Now the question may come like this on this graph. What does the slope of this graph indicate? Slope is to divide stress upon strain. You say determines the elasticity of the body, elasticity, or modulus of elasticity of the body. If question comes, what does the area of stress strain curve indicate? What does the area indicate? Area of stress strain curve. Area of stress strain curve. Strain curve will be equal to, you can see, if you find the area out here, area will be half into base into height, that is half into stress into strain will come. And what will it represent? It will represent this thing. We got the elastic energy per unit volume. Elastic energy per unit we have another topic is called thermal stress. Thermal stress. What is called thermal stress? Stress is means force upon area. Okay. Thermal stress is related to temperature rise. When we heat a substance, we find there is a elongation taking place in it. The length of the body here also increases. And when you cool it, the length decreases. That is also somewhat elastic in nature. So the stress which you measure due to temperature is called thermal stress. And we are finding a formula for it. Okay. And the formula goes on like this. See, alpha is called coefficient of linear expansion. Coefficient of linear expansion. Linear expansion. Length expansion, that means. Length expansion. Coefficient of linear expansion. So alpha formula means change in the length per original length per degree rise of temperature. Theta. This ratio is called alpha. I think class 9 this topic was there. Linear expansion, superficial expansion and volume expansion. So learn about the linear expansion. The alpha is equal to delta L by L theta we will write first. Right, alpha delta L by L is called strain. Strain by theta. Therefore, strain value will become alpha into theta. Strain value is becoming alpha theta. And we know the formula of Y. Y formula is what? Stress by strain. Stress by strain. When this tensile stress belongs to the lengthwise stress and lengthwise strain. So we write stress is equal to Y into the strain. Cross multiply. Right here stress is equal to Y into strain value input, and strain value is alpha theta. Such stress is related to temperature, no? Temperature rise. Such a stress is called thermal stress. Therefore, we write thermal stress is equal to Y alpha theta. This is the formula of thermal stress. And now the last part of this chapter is called force elongation graph. Force elongation or extension graph. Force elongation graph. We take elongation here this time. Delta L is taken here and force we are giving here like this. So within the elastic limit we are directly close to the graph will come like this. Within the elastic limit, suppose the point starting point is 0 and the end point is A. So the region, if I write this part is O, suppose O, point O, OA will represent the elastic limit. Means within this the body will be perfectly elastic. The body will return back to its original shape and size. And on further applying force, we find there will be kinks formed like this way, wrinkles formed like this. And then that this will happen. Between A to B, kinks are formed or wrinkles are formed. The point where the kinks vanishes, formation of kink stops, that point is called yield point. Y-I-E-L-D, yield point. Yield point. The point B is yield point, where the kink formation stops. So, a matter of common, let us take a rubber strain. Stretch, you see, small linings are formed in there. When you stretch, we apply too much force there again. So, they are called kinks. When the formation of kink stops, then we call it yield point. And beyond the yield point, suppose we are having a point C, the body becomes plastic. If you further apply it, it remains strained. It never comes back. It does not come back. It remains elongated. It does not return back. The body becomes plastic. That is, between the region B to C, the body acquires the property of plasticity. Between B to C, the body becomes plastic. Plastic is not returning ability. It will not be able to return. And now beyond this, further you apply the force. On further application of the force B, the body will be braking. This is called braking. This is such a force at which the body brakes. This is called braking force. This is called braking force, which will be braking the body. Then after the body becomes plastic, so there is a very high chance that the body breaks. So if you stretch a rubber cord like this, too much stretch will break the rubber cord. So this kind of graph we get for between force and elongation. Actually, so O2A represents elastic limit, formation of kink when it stops. After beyond this, formation of kink takes place, and the point where the kink formation stops, that point is called yield point. And beyond that, the body becomes plastic. On further applying force, the body breaks. So the force which causes the body to break, such a force is called braking force. And if the force is acting per unit area, so that stress is called braking stress. For this braking force upon area will be called braking stress. So this was the theory part of this chapter. So next day we will be doing problems, numerical.